Hi, my name is Wes Auker. I'm an electron microscopist at MCO, Penn State University, and today we're going to be taking a look at some post-processing, specifically with EM images. So we're going to start this off with what I have here is a panoramic of solder, and nothing was done with this. It wasn't polished. This is actually preheated, so this is solder right off the spool. And with an image like this, quantifying structures and trying to get underneath and pull data out of this can be pretty challenging. Post-processing is typically used, or at least most often reached for particle counting, pore counting, but with more complex structures and network structures like this, you face a couple of challenges with that. So firstly, let's just take a look at a basic head count. Is this one complete network of lead? How many individual networks are there? What's the largest one? In this case, I'm using FIJI or image J for this work, and I'm getting a count of 161. We can get circularity, average area, farad diameter, and total percent area, which is about 50% of the image. So the next question would be, how does this look? Like, how visually can I tell with this network what the biggest backbone is? And also it can give me a handle on eliminating noise and applying filters to get smaller pieces of lead out of the frame. Anything that I don't think would be useful in the analysis. So we can see from that orange area, it's obviously the largest backbone in this structure. And this particular plugin in FIJI is called Connected Component Labeling, which was originally designed for bone tissue analysis, but there's no reason in this instance I can't use it to evaluate lead. So the next question would be, how do we get a handle on lengths of these various lobes and these networks? And one good approach in FIJI would be to skeletonize the network. That starts to give us a handle on segment lengths, number of triple points, number of junctions, and it can be pretty useful as far as trying to get a handle on that. But it doesn't necessarily tell you what the longest lengths are going to be. For that, we can use longest path calculations, where we take that skeletonization and we just start working the problem. And basically, with this kind of calculation, the path length can't go in circles, and it can't retrace pathways. So it might look like there's some areas that have been ignored here, but in reality, that's just the one-shot nature of longest path calculation, which in this case is about a half a millimeter. All right, next we're going to look at thickness of these lead grains. And basically, these are continuous measurements. These are distance maps, and these are a couple different types. On the upper right, we have what's called a geometric distance map, and on the bottom, it's called a ridge map. Now, they're not built quite the same way, but basically, you're getting continuous values out of this. So these aren't discrete measurements, but I can give you a handle on like what's an average thickness of these lobes, which in this case, it's somewhere in the neighborhood of 6 microns, 6.6 actually. Another alternative for measuring thicknesses would be watershedding these networks, which shatters everything apart into pieces. What the software is looking for, FIJI is looking for in this case, are pinch points with those bright lead grains. Anywhere where those pixels get close together, it's going to draw a line and do a break. So these are discrete measurements, and at that point I can work to start to get average diameters of each one of these individual pieces. In this case, there's about 1,400. So now here I'm getting a little bit smaller diameter, about 5 microns, probably because there's areas in the network that are being over-segmented into very, very, very small fragments. So that could be pulling my statistics down. Now you can apply filters here, but of course you could apply a filter and force it to give you the exact result that you're looking for. And in this case, I didn't want to do that. I just wanted to one-shot it and see how close I could get to 6.6 microns with this approach. So now we're going to do three-dimensional reconstruction with at least a small portion of the lead network, and on this video what you're seeing is a series of 500 slices just moving through, and now I'm at a 52-degree angle, and I'm doing this on a dual beam FIB. So let me back up here a moment, and let me just point out this is the field of view that I want to do the reconstruction in, and what I care about in this instance is the tin background, my lead grains, and most importantly this gap, these really dark spaces in between, which isn't the same all the way around the grain. There's areas where it's tighter and areas where you obviously have a greater gap here. So that's what I'm going to be looking to reconstruct here in the following images. So those 500 slices give me an original grayscale volume. They give me my tin volume. They give me the lead volume and the void volume as well. That's that space between the tin and the lead itself. And you can pull a lot of analytics out here: surface area, total volume, and diameters and things of that nature. Putting that all together and then adjusting transparency for the tin itself allows you to get a better visual handle on how these voids are evolving and progressing through the lead matrix. Now this is, while useful, it doesn't actually tell you how these voids are behaving in terms of change in volume. For that, I can get a volume map, which is kind of similar to the thickness heat maps and distance maps, except in this case we're operating 3 dimensions. And I can see that this lobe here and this top section of the grain are the biggest violators. That's where these voids are really starting to get aggressive and starting to potentially could cause problems in this lead network. And here, total overlay just gives me a handle on, relative to that lead, where I'm looking at these voids are occurring. And this could be an indicator that lead, at least with these grains, starting to break down, could present structural problems. Heating could cause inclusions or other things that could give problems in circuitry. So, and that is it. That is my presentation on EM post-processing.